good to go.
All right, let me begin by sharing my screen a little bit in here. You had a chance to see my real face and can watch it there on the sides a little bit. But I'd like to give you kind of a presentation about icebergs as a remote sensing story on this. So I used to work for NASA, the Jet Propulsion Laboratory, before I went to work for Brigham Young University. And when the NASA bigwigs would come down, we put on our shirts and ties, and we put on what we call the dog and pony show. Now that my wife lives in rural, not really rural, but in Utah, my wife raised miniature horses. So these are some of our miniature horses we have here. And so I think you guys are VIPs, so you deserve a dog and pony show. So here it is. Okay. So, just to introduce myself a little bit, I've been at BYU since I left NASA for over 30 years. I'm a professor of electrical and computer engineering. I specialize in microwave remote sensing. And I still do a lot of work for NASA working on these teams, and I'll tell you a little about some of that research as we go. So I've had the opportunity to work on a lot of NASA projects over the years. I was a system engineer for a series of scatterometers that flew into space. So I was involved in the launch of 3 major missions and a bunch of smaller ones. And so here's one of the videos of the launch of one of our spacecraft. This happens to be the NASA scatterometer, NSCAT. And we've flown some of these same scatterometer instruments on multiple spacecraft and missions, and had a lot of fun doing these projects. When this video first appeared, this is like the first time anyone ever seen a live video from a spacecraft. Now we see this a lot on SpaceX, but 25 years ago, this was pretty new and spectacular. Nowadays, of course, I do student launches, trying to get my students out into space, and well, not into space, but into the aerospace industry and in doing engineering sorts of things. I like to point out there's no such thing as a rocket scientist. We're all rocket engineers. So we're really doing about engineering. So some of these slides are from my kind of outreach programs here, and this is one of my favorite slides to talk about. That as an engineer, we solve problems on Earth. So I'm going to talk about remote sensing. Remote sensing, of course, is seeing from a distance. So we have a chance to see things from a long way away. So we are already expert remote sensors because we can see things from a distance now. We use our eyes to do things. Now we have modern technology that, like cameras and telescopes and radar, that we can use to see things from even further away. So this is Utah from space, but we usually think about remote sensing, something happens far, far away. But as we move in closer to our Earth, things begin to seem a little closer and closer till we finally get to a human view of that. Well, this is all possible because of the electromagnetic spectrum. I'm preaching to the choir a little bit, but you'll forgive me. The electromagnetic spectrum extends from very low frequencies up to very high frequencies. In the middle of that is the visible light spectrum, which we're used to seeing at. That's where we're expert remote sensors. As we look at the different wavelengths and frequencies, those correspond to different colors of light. And I like to use as an example that we see different things at different colors of light. So here's a picture of me seeing at different colors of light, red and blue. And my mother says that God must have loved me because he gave me lots of sun kisses or freckles. Those have faded as I've gotten older. But when I look at me under blue light, I can still see those freckles just fine, whereas under red light, which is the color of freckles, they're not as visible. Well, we can use that same idea in looking at other parts of the electromagnetic spectrum. These represent other colors of light. And so I'm going to focus on microwaves, which are frequencies that have wavelengths that correspond to something I can show with my fingers in my hands, rather than the really tiny values that we see for visible light. And when we use radar, we provide our own illumination. So it gives us a chance to see the Earth in a different way than we're used to seeing with our visible light spectrum. So microwave remote sensing radars are really nice because they can see through clouds, they can see through dust storms, they work just fine at night. And the wavelength we're looking at, the different color of light, allows us to see the world a different way. So you can see on this spinning globe that the South Pole and North Pole are very bright due to their ice coverage in the radar, and that jungle regions are very light, whereas dark regions correspond to deserts over the Earth's surface. So understanding and seeing these pictures can really help us to see what's going on here. Now, one of the missions that I worked on, in fact, I was the experiment manager, the guy who actually wrote the proposal to get the money from NASA to do that, to do the actual project, was called the SeaWinds scatterometer on QuikSCAT. And it was a dual pencil beam scatterometer that measured the reflection of the Earth's surface. I'm going to talk more about this. This spacecraft was about the size of your bedroom. It would fit in your bedroom. The antenna dish on that is about 1 meter in diameter, and it rotated about 18 RPM. I'll show you an animation where it actually worked. This particular system was part of a larger mission to measure the surface roughness from space. So here's that spinning scatterometer. It rotated about that speed as that spacecraft moved along. And it was designed to measure the backscatter from the surface of the ocean. So here's what the ocean looked like. It's covered with waves. Now, the ocean's pretty complex. So, but if we break it down, it really consists of lots of different wavelengths present, water wavelengths in there. The radar broadcasts signals toward the ocean surface. And if you ever stood on the ocean surface and watched, I'm sorry, the shore surface, like on a quay or a dock, you watch the wind blow, and you could see these little waves that are created. That little surface roughening is called cat's paws, and those are surface capillary wavelengths that are about the size of the radar wavelength. And so we get Bragg scattering. So when we look at the surface with those waves on the surface, when we look in different directions, we get a different backscatter from the surface. We can use that to retrieve the wind speed and the wind direction over the ocean surface. That's one of the things we're going to talk about. And this is a really good example of interdisciplinary research because we do science with it, and we have all the engineering and principles going together. So this is an animation of a series of optical images of Hurricane Isabel, which struck the east coast of the United States in 1999. And we're seeing 1 day's worth of images in this sequence. Now, we're seeing the cloud tops in this image, but all the destruction occurs at the surface level. Fortunately, QuikSCAT was operating at the same time and could actually make radar measurements through that thing. And so its measurements were shown here. So this is that same area up in here. And each one of these colored vectors represents one wind speed and wind direction measured by one pass of this radar instrument as it passed overhead. The color here shows the wind speed, and the arrows then show the direction. This was really amazing to weather forecasters because we were able to provide them with a wind measurement over the ocean about every 25 kilometers. Over this grid. They almost didn't know what to do with it. You see, the problem with weather forecasting is in order to predict the weather in the future, you have to know where the weather is today. And over the ocean, we don't have very good measurements, especially of wind, which is so important in that. Well, when I came to BYU, we decided we wanted to try and use the radar data for other things. And so we began applying our signal processing techniques to look at this data to see if we could produce higher resolution measurements. In this picture, the little black flags represent the wind speed, and the number of tails on the flag show us the speed. And the color background represents an enhanced resolution image based on the radar backscatter looking at this thing. And we can now provide wind measurements at the order of a few kilometer resolution. And we can even resolve the eye of the hurricane, where the wind speed drops low. So this is really intense, greater than 50 knot wind speeds, intense wind damage going on here, and we can resolve that eye. And as a result of this, we've been able to explore the use of the scatterometer to even produce higher resolution data. So often on the right here, this is a standard resolution map produced by the scatterometer. It's about 25 kilometer little boxes up in there. When we enhance it, we can look over to the left and we get much finer resolution. We can resolve the eyes. We can see the comma clouds, the rain bands that occur up in here. And even some of the stuff that looks kind of like noise, we realize, well, these are thunderstorms. that are on the periphery of the storm. This is a kind of an image that shows the track of all the hurricanes that hit the United States over a 50-year period, up until just recently. And you can see how many times the United States, North America, gets hit by these hurricanes, even though a lot of them end up just dissipating in the Atlantic Ocean. So we processed all the hurricanes that occurred during the QuikSCAT era and made them available for researchers to study and help them in predicting their occurrence. Here's kind of a zoom in on this. Forecasters are really interested in knowing the center of the storm. So they use the cloud top images, but sometimes those are a little off because it's hard to resolve the center of the cloud very well. Our winds really help, but until we get to the really fine resolution, we were able to locate the hurricane centers to within a 1 or 2 kilometer resolution, which is very important, especially when you're further out in the Atlantic Ocean where the airplanes can't fly to make weather measurements and predictions. So this shows an example of, for Hurricane Isabel back in 1999. I know it's a long time ago. I should use something modern. But it shows all the times that the QuikSCAT hit this scatterometer as it flew along. And we can show an animation of each one of the scatterometer passes over that storm before it slammed into the coast. This is a remarkable set of series to show how useful this instrument, which is designed to measure winds, can be. But the scatterometer makes measurements over land. We don't use them for wind, okay, because there's no water out there necessarily, but we can look at it for other purposes. So let me illustrate one of those purposes. This is a radar backscatter image of northern South America. The bright area here is the rainforest, and you can see the lighter area is the jungle part up there. When you look off to this darker area here, this is the savanna regions up in here. We compared an image made by the QuikSCAT, by InSCAT, with an image created 20 years earlier by the CSAT scatterometer, which was the first scatter that ever flew into space. And we colored the areas that have significant change, yellow for a little bit of change, and pink for a lot of change. We can ignore what's going on in the mountain areas because that's where snow falls and it melts, and that changes every year. Also, along the riverbed, the rivers meander and change a little bit, so we can kind of neglect that. But what about the rest of them? Well, this dot right up here, this is where the Brazilian government dammed up a river, the Manaus River, and this is when a lake was created by that. Interestingly enough, if you look at the line, you can see a kind of a line here and a line there, and a big patch. This is where the Brazilian government put up roads. And so people will go up into the Amazon, cut down the rainforest, farm it for a few years, exhaust the soil, and then move on. And so these represent areas of significant deforestation in the Amazon. This is the city of Sao Paulo. If you've ever seen the movie Up, you know, where they have the mountains of the rainfall and the clouds, that's really a true place. And that's right here. Okay, that place that he saw in that movie was there. Well, here's a kind of an image of that we made of looking at multiple frequencies in Antarctica, and you can see some things. I'm going to talk about this picture later, so I'm going to save this for later. But what does all this have to do with icebergs? Well, this is the fun part of the story. Okay, so you know, back in the early part of the 1900s. A ship named the Titanic was floating through the ocean, and of course it ran into an iceberg and sank, and a really fancy movie was made of this, and so we could talk about all this. As a result of this tragedy where a lot of people died, the governments of the world got together and formed the International Iceberg Patrol, which is where people would track and radio in the positions of icebergs to help prevent that from happening again. But sometimes they lose a few. Here is a picture that was collected from the very first data, the very first day of data that we collected from that SeaWinds scatterometer, QuikSCAT. And it shows Antarctica, which shows up very bright because there's a lot of backscatter, a lot of volume backscatter. The signal penetrates the snow and reflects from all those snow layers coming back, gives us a very bright return. Around the outside is sea ice. I've removed the ocean ice. But in making this picture, we noticed that there was an extra island here that didn't belong. which turned out to be an iceberg, and it was in the Drake Passage, which is where ships pass through. So a lot of ships pass through this area. So the interesting part of the story is I was at JPL where we were actually processing the data, and this image popped up in the processing, and I turned to one of my graduate students and said, "Hey, look at this, there's an iceberg out here." And he said, "Well, shouldn't you tell somebody?" And I said, "Oh, the National Ice Center, they track those things." A few days later, I called them up because I wanted to find the name of this iceberg. And there's a lot of flurry and activity and things going on, the rustling of papers and people running around and talking. And they said, "Where is this?" And I told them where it was. "Well, this is an iceberg that we lost track of. It was originally down here, and it started to move into the ice pack. And then due to the darkness and the ice and everything, people weren't able to keep track of it. The iceberg moved out into this area and now was a shipping hazard. So they did a press release on this to announce this iceberg here." It probably is a good sign that it says that professors should occasionally listen to their graduate students. So here is an animation of the movement of that iceberg, B10A. And you're looking at one picture per day created by the scatterometer. And you can watch this iceberg and another iceberg, A22B, move around like a couple of dancing paramecium up toward South Georgia Island. This is the island of Shackleton fame. And we tracked this iceberg ever since then. Here is the only satellite optical image of that iceberg ever corrected from that time. To help put this in perspective, this iceberg is 66 nautical miles long and about 25 nautical miles wide at its widest. If we zoom in on the lower corner of this, down at the bottom, the little dandruff that we can see here, the little bergy bits, and that's the technical term for these icebergs are actually 1 kilometer in size. So even these little tiny pieces are huge for this iceberg. The little pattern you can see on the iceberg here is from the flow as it flowed out into the ocean. Well, one of the other things we see is besides the icebergs, we can watch the growth of the sea ice. And so there's something to be learned by looking at this data. Let's see what we can do. The National Ice Center was so impressed with our ability to track these icebergs on a daily basis that BYU became a primary source of information for tracking Antarctic icebergs for the National Ice Center for the next 25 years. So we provided this tracking information, and it turned out the astronauts on the International Space Station are really enamored with taking pictures of the Earth, and they especially like icebergs. So we'd provide information of where this iceberg was, and they would take photographs. So here's a astronaut-created optical photograph, just taken with a handheld camera using a telephoto lens from the space station, of an iceberg that we pointed out told them where to look. This iceberg was 25 miles long by 12 miles wide, and about 300 meters thick. Now, how do we know that? Because the iceberg raises about 30 meters up from the surface, but 9/10 of the iceberg is below the surface. Well, we've been studying these icebergs because they act as a proxy for the breakup of ice shelves in Antarctica. So we can kind of watch their melting and the breakup and how they disintegrate. That helps us understand how some of the ice sheets in Antarctica disintegrate. So here's an example of that particular iceberg. This is a 20-meter high iceberg that we helped a ship navigate to there. The problem is the icebergs can move so fast, and the ships, they move almost as fast as the ships. And so it's hard to direct the ships to the right spot. This iceberg, you can see the actual layers in the icebergs. And since it's 60 feet high, more than 600 feet deep, this iceberg goes down below. So we've been, as we were doing this kind of work, people were pointing out, well, there's a lot more icebergs, especially in Antarctica, than there used to be. Maybe this is evidence of climate change. And in particular, this image is a optical image collected from satellites of a summertime view of the Antarctic Peninsula. That's this area right here. This is the mountains, and around it is what used to be a permanent ice sheet. This was the Larsen ice shelf. It was several hundred meters thick, and we watched in horror as this ice sheet suddenly disintegrated. And so I have pictures of this, and we could see the actual causes of this because it got warmed due to climate change. Well, are all icebergs due to climate change? So here is another animation of that area. This is the Antarctic Peninsula, the picture I just showed you. This area here is the Antarctic Peninsula. This area is where it broke up. This is the south end of South America, the tip there, South America. This is South Georgia Island. This is Elephant Island of Shackleton fame, some other islands up in here. And these circled dots here represent icebergs that are being moved by currents and wind in the ocean. You can watch the annual cycle as the ice freezes up and then melts backwards up in there. And this radar data is particularly useful for tracking the icebergs because it's not affected by either the weather or by the sunlit areas up here. So one of the problems with using optical sensors, that image I showed you before, is that most of the iceberg is actually covered by clouds. And this area is very cloud covered up in here, so it'd be difficult to track the icebergs. So we began doing this, and we went back and looked at all the radar data we could find to identify every iceberg. So I had students looking at icebergs for years looking at this. And we created the world's largest database of icebergs. And this is a plot of icebergs in Antarctica, around Antarctica, dating back from the early 70s up till 2010, and we've continued up into the present. But this is the important part of the thing. The colored lines represent different sensors, okay? All the sensors except for the blue one are radar sensors. The blue one is actually the National Ice Center's database. It started with a low number back in the 70s, and then it climbed almost exponentially. So by 2000, when the question was asked, does this exponential increase represent a sign of global warming? People were wondering that. So we have our first radar observations from the CSAT scatterometers back in 1978, and the count for these major large icebergs was about 12. So the National Ice Center was undercounting, significantly undercounting that time. In the late 80s, they added optical sensors, a new kind of an optical sensors, and their count went up. So this count here is actually attributed to the fact they undercounted here, then they got a better sensor and they started counting them. So for the next 10 years or so, their counts were consistent. And so some of the European remote sensing satellite scatterometer, ERS-1, went online. The optical counts and the radar counts were the same. In 1996, we launched a new sensor, the NASA scatterometer. At the same time, coincidentally, there was a major calving of icebergs off of one of the ice sheets from the Ross ice shelf. And so we saw a jump in icebergs. Okay. Then again, in 2001, we saw another jump in icebergs. This one was observed by QuikSCAT, but the National Ice Center was also seeing these as well. Well, this suggests there really are more icebergs coming up, and in fact, we saw there more icebergs than even they could track. So this was a dramatic increase. What does that mean? Well, about every 50 or 60 years, there's a major calving off the Ross ice shelf or the Irani ice shelf in Antarctica, which happened about every 50 or 60 years. And the last time it happened was about 50 or 60 years ago. So this is actually consistent with what we saw. So when we look at the details here, while there's evidence of localized warming in Antarctica that actually led to the breakup of the ice shelf that I showed you a minute ago, there's really no evidence from the iceberg count itself that the icebergs show there's any global warming. Now that was true through 2010. However, more recently, we've seen a lot of ice sheets break up that haven't broke up. The largest ice shelf is totally gone now. The last one broke up, the last chunk of that broke up just this last winter, and we've seen a lot of icebergs coming up there, and those are caused by melting underneath the ice shelf. So the situation has changed. In order to really understand if there's climate change that we can observe by radar observations, let's turn to Greenland. Now, Greenland is the largest island in the world. Okay, the ice at the center is more than a mile thick, but it's so heavy, it's actually depressed the center of the island. So if the ice actually all melted, it would be an archipelago just around the ice, around the outskirts of the island. The island is so high, the snow is accumulated so high on this island that the snow at the top basically never melts. But that pressure causes the ice to flow, and that forms glaciers that flow out to the sides of the island. So on the edges of this mound of snow, as it flows off, we get some melting as it drops lower. And as the snow melts in the summer, the snow will percolate down into the water, melted water will percolate down into the snow and refreeze. Further down, the snow will get saturated, and then we'll see some formation of lakes. Even further down, the snow will completely melt off, the annual snowfall, and you'll see bare ice and then eventually rock. So this is sort of a cutaway profile of what what Greenland looks like. Here is a summer image collected with C-band data from the ASCAT scatterometer, from KU band, from the QuikSCAT scatterometer. And you can see in the radar data a very bright band that's white here and a kind of a golden color up in here. The golden color changes due to the amount of accumulation of snow in different areas, regimes, or melting basins for this. Around the edge, you can see a darker band. This is where the actual snow is melted and ice. This shows where the bare ice region is. And in fact, by looking very carefully at the temporal evolution of the backscatter, we can actually map the different regimes we see here in this profile on these mapping things. Okay, so if I take that summer view and spread it out and use the census we have from 1978 to 2008, so this is a 20-year period, which we've now extended even further. I'll show you a little later. This is an anomaly plot where I show the difference in the melting from the average for each of these years. Okay, so we're seeing a change in the radar backscatter at KU band. We see more melting as evidenced by greater changes, that is, there's more melting around the outside of the island in more recent decades. Paradoxically, we see more accumulation. That is, the darker area in the center corresponds to more accumulated snow. So there's more accumulation and more melting. Well, how does that work? Well, that's actually consistent with a global warming world, because warming causes more evaporation that causes more snowfall. So that's consistent with more accumulation. The warming clearly results in more melting. So how does that actually work? Well, we point out that the climate is always changing. There's a lot of interrelated effects. There's random effects like volcanoes, there's natural cycles through the sun, and then more recently, there's human effects. Sea ice gives us a measure of that because it tells us how much the warming is. So this is a northern hemisphere view of the polar cap. And the median ice edge is shown with sort of the pink. That's our median over the last 30 years we've been observing of that. Well, satellites have provided us a new view of that. If we kind of go back to what's going on from a climate perspective, over the poles, the Earth freezes. That freezing water, which is actually the ice, cools the water. Well, ice water doesn't freeze. As it starts to freeze, the ice is forced out. That sinks to the bottom. That flows along the bottom of the ocean, and it rises near the equator to warm up, and then goes back. That warm water coming back keeps the polar regions warm and the tropical regions cooler. This is called the thermohaline solution. Just the salt water sinking due to freezing at the poles and then warming up. A lot of that actually occurs down in Antarctica. Okay, what's going on in this area that we looked at before is where Antarctic bottom water is formed that flows along the bottom, saltier than the regular ocean, then it comes up near the equator where it warms up. So if we look at the sea ice, now we're looking at a movie over multiple years of the growth of the sea ice due to freezing. That's the formation of Antarctic period. Then it'll melt back. If you look very carefully, you can see there's kind of a flow, and that's due to katabatic winds blowing the ice away from the ice sheet, from the continent. A couple icebergs dancing around up here. You can see some more up here. And this pulsing is due to katabatic windstorms pushing the ice away, forming Antarctic bottom water here and right there. That sinks to the bottom and flows along the bottom, comes up. The ice sheet melts back, then it reforms year after year. In Antarctica, we don't see a lot of change in the amount of ice cover, so that's not really changing very much. But in the Arctic, we're seeing a lot of change. So let me advance this to the next thing. If I look at the Arctic, here's the same movie of the Arctic. Now in the Arctic, things are a little different. There's a permanent ice cap. It doesn't melt back every year like it does in the Arctic, in the Antarctic. This permanent ice cap survives the summer. So here's the summer, now it's going to regrow. And that period in the middle gets very thick. So the ice in the core may be as much as 17 meters thick, whereas this new ice, which is darker in the radar images, is perhaps much thinner and melts back during that time period. This permanent ice pack is much thicker, insulates the ice water, the ocean, from the cold air mass. As we watch the cycles, we watch the warm fronts pass over and melt the ice sheet and the surface of the ice sheet, which then changes the albedo of the ice. And so you get more positive feedback, which is causing more melting. Well, that also produces Antarctic bottom water, which then flows through the Fram Strait down into the Arctic Ocean, and is one of the things that helps drive the Gulf current, which brings warm water from the Atlantic, the South Atlantic, up into the North Atlantic up in here, where it melts this. Well, we can also see the advection or movement of this multi-year ice along the east coast of Greenland, which is also thinning the ice sheet. So we have not only melting, but the movement of this, which is driven by the oscillating climate system, the North Atlantic oscillation up in there. If you look, you can see the changes in Greenland melting around the side. You see some big glaciers in Iceland, also some glaciers along in the Baffin Island up in here as you watch the cycle. Looking at, say, Siberia up in here, when Siberia is frozen, it's very bright because you get a lot of reflection from the frozen area. So it's very bright, but when it melts back, it turns golden when it's frozen. But when it melts back, it turns gray when all the different frequencies we're looking at the scatterometers melt. So this is the frozen tundra up there, and then as we watch the movie, it will cycle and become unfrozen cycle. So we can use this data to map the spatial extent of the multi-year ice, which has one insulating property, and the first-year ice. So that's the next thing we do. Well, since I'm talking to a bunch of scientists and engineers, I can actually describe the methodology a little bit. If I plot just a histogram of the brightness that you just saw for each day, so I produce a histogram. So this is the histogram showing the radar backscatter for one day, and then I do it for each day of the year. So I make one and then stack them up. I get this general pattern. And if I tilt that histogram up and look at it from the top, now the color tells me how high the histogram is. It tells me how many pixels are covered with ice. During the summer, not very much of the ocean is covered with ice. So all the ice that survives is by definition multi-year ice, okay? The multi-year ice extends along here. It doesn't change by brightness very much. We saw those weird patterns come, that was right here, but when that refreezes, it stays up here all winter, okay? It drops a little bit due to the accumulation of snow at the top of the ice. But we see the melting of the first year, or the formation of the first year ice as it freezes, and it starts to dominate the total histogram. That is, a lot of the ocean is covered with ice. Okay, so you see all this ice down here, so percentage-wise, these normalized histograms, this starts to dominate. So I can easily classify first-year and multi-year ice by just drawing a line at the backscatter up here. And so I have multi-year ice up here, first-year ice down here, and I can just map the pixels of that and create a time series. So here is that histogram now extended to multiple years. during the QuikSCAT era. And you can see the decline, the amount of multi-year ice with time, and the decline of the first year ice, where it goes. That's not so obvious to me, David. Well, let's take a look at it. If I just map the number of pixels covered by ice, and just one time at a time, here is that annual cycle over a decade, almost a decade, and we see that the winter maximum basically, I'm sorry, the summer, I'm sorry, winter maximum, basically the same. That's what I mean. Yeah, the winter maximum is about the same from year to year. But look at the summer minimum. It starts off here, and as we extend down here, we see that, especially in this winter, the 2008-2007 winter, there was a dramatic drop in the coverage. So we actually did a linear trend in the ice reduction up in here. And it's because of the reduction in multi-year ice and the melting and the not as much of the first year ice. To extend that to kind of show that, here's the classified areas here. This is from 2003 down to 2009. The light cyan represents first year ice, the white represents the multi-year thick ice. And we can see the reduction in the multi-year ice, even though the winter extrema is about the same. If I'm sorry, I had some more slides that I must have commented out that show this happening over more decades up to the present. But I wanted to also talk a little about some of the radar, since you guys are playing with synthetic aperture radar up there. I wanted to talk a little bit about our radar experience that we're doing here, where we do aircraft-borne SAR a little bit here. So this shows the history of radar that we've had at BYU. And we started out with building large radars. When I came from JPL, the radars we were building were in DC-8s, and the radar we had there occupied a third of a DC-8. If you can imagine that. So we decided to build smaller ones at BYU. So first it occupied a couple of passenger seats, and then we built one that we could hold in our hand, and then a little more elaborate ones that are basically the size of cigar boxes. And we fly them on these planes, looking at sea ice and land observations. So I'll show you just a couple of them. We flew one of our radars on a drone that we flew out, UAV that we flew out from Svalbard north into the Arctic Ocean during the melting season. We were trying to understand the difference between sea ice seen in radar and optical images. So here's an example of that. Here's the radar image. Liquid water looks very dark. Ice is lighter, but we can't tell the difference between a melt pond, which is a water that's sitting on the ice, or open ocean. So we also took co-located camera images. So these are camera images of the same basic areas. And these show that the ponds, the dark areas that we see in the radar, are also open ocean. That's great. But here, what looks like it's melting is actually a melt pond on a big ice floe. So if we use the radar to map the amount of melting here, we might actually overcount the melting, because we would say that's over. We'd say it's definitely melted, but we would think it's maybe open ocean instead of a melt pond. Here's a couple of other images that we worked with, showing how we would take multiple passes to continually map that. So here's one pass and another. We can put them together in Google Earth to sort of display that. And we worked on ways of advancing our processing. We've made this data available for others who want to practice doing SAR processing data. We have MATLAB code and data that's available online so that you can use the data to practice your favorite algorithms. And we see people using our data. You can see the melt ponds and this kind of thing. So that kind of summarizes it. Okay, let me just talk a little bit about some of our work in the aircraft-borne SAR system here. So this represents one of the smaller radars that we built. A interferometric radar. So it had a baseline in it, so we could measure topography as well as images. And here's an example of what we did. This is showing some examples of an X-band SAR, one of our early radars that had a meter resolution. And this shows the topography that we derived from it. Then we overlaid the image over that. So you can see it's flying along, and you could see the radar imagery from the vegetation is very bright, and the topography that we extracted from that. So this is one of our experiments that we did back in the 1990s. And that got us thinking about trying to make smaller radars and other applications of radar. So we built a 3D imaging radar, which we used to image trees. So this is a very short range radar that we just took an image of this tree, and this shows the 3 different views of that tree that we were trying to study how the scattering works from leaves and branches up in that. So we made a couple of images up here. This one was kind of fun and interesting. This is the front view. We didn't realize when we made it, the tree was damaged. So when we looked at it from the front, here's what it looks like. When we looked from the side, we found out it was missing a back half. And sure enough, we went around and looked at it, and there was a tree that had fallen off the branch and broken off in a winter storm or something like that. And so this has helped us in sort of our theoretical modeling of trees. There's my summary of my talk. Kind of went through it very quickly so that I could leave some time for question and answers. So I'm going to just turn the time back to you for, well, if you have any questions, I'm happy to help. I can go back.
So I have one question that I kind of missed in the flow of information, which is how much do these results change with the wavelength of the SAR imagery?
Okay, well, I've got a really good answer for that one that I can show you. Let me pull back here to this one that I showed earlier. I told you I'd talk about a little later, which is this picture of Antarctica. Okay, this is actually an RGB image. It's artificially colored. Okay, so the red is horizontal polarization, QuikSCAT. The green is vertical polarization. The blue is ASCAT C-band. So this represents 5.6 centimeters, like that. Okay. So you can see it there. The other one represents K-band. That would be about about an inch, about 2.1 centimeters. So that's the difference between the two. 10 centimeters to that. Okay. Now, if you look at the ocean's very dark and kind of bluish colored here. That's because ASCAT gives you a fairly strong return from the ocean, but the resonant frequencies are much stronger and brighter, so that it looks brighter at KU band. So the ocean's darker out there, but that gives me more dynamic range to measure the wind more accurately. So the higher wavelength, the higher frequency, the shorter wavelength is better for measuring winds because I have a better dynamic range. Okay, but the longer wavelengths penetrates the ice differently. So if you look, you see a lot more variation in color in the ice. This golden color is because the blue and the red are mostly providing information, and I can see this purplish color is the ice is only a meter or two thick here, so you're seeing the water below the ice in the C-band data. It's more penetration, and then we can discriminate. So this is multi-year ice in Antarctica. This is rough first-year ice, and this is smooth first-year ice that was just formed by the pulsing of the katabatic winds pushing it away. So this is the stuff that forms Antarctic bottom water. And the little bright dots in there are icebergs, and they're bright because they've had surface melting that's given a lot of frozen ice bodies right underneath the surface. And so all the frequencies respond equally well, so they look white. So here's a practical implication of the difference in the wavelength. The lower the wavelength, the greater penetration you're going to get in vegetation and in snow and ice. But as soon as you have any water at all, you get no penetration at any frequency. So let me flip ahead to Greenland for a second here. And here's that same kind of image in Greenland. Notice that the land area here, which is now bare land and vegetation, looks kind of purplish, which means the blue has a very strong return, and the green doesn't have a strong return. It's that the V pole is responding differently than the H pole, giving us a different color. A lot of the satellite SARs operate at L band, so they use much longer, foot-long wavelengths. Okay, at 1 gigahertz, so they get even more penetration. So CERC, the radar sat, they're operated at C-band. CERC went down to L-band. TerraSAR X operates at X-band.
Okay, thank you. So is anybody planning to put up a vehicle that actually uses multiple bands to get basically the equivalent of this kind of work without having to compare different satellites?
CERC carried an L-band, a C-band, and an X-band SAR on the same platform, the shuttle, but it flew a limited time. No other satellite that I'm aware of has carried a multi-frequency SAR. They've had TerraSAR X, which is flown by the Europeans, is a very nice X-band SAR. And then they flew a second one, so they fly in tandem. So they call it Tandem X now. So they do interferometry, both a long track and cross track. And I didn't show anything on long track, but a long track allows you to measure velocity. So you can see ships in motion and traffic on roads and watch currents and winds blow over the ocean. Bob.
So
I'm sorry, it's breaking up. I'm not hearing your question.
I'll bring in another microphone. Hopefully
much better. Yeah, that's clear. Yeah.
Okay, so wanted to thank you. It's very remarkable stuff to look at, but very sobering at the same time.
Yeah, the change.
I was just wondering, where are you or your former students taking this? What's the next steps?
So me and my group are most of what I would call observationalists. So we're developing the technology and we're making the observations, then we turn the data over to the scientists. So all this, all the imagery, all that scatterometer imagery is available on my website, the Scatterometer Climate Record Pathfinder, www.scp.byu.edu. And so you can download the data and use it. So we process every scatterometer data that's ever flown that we get the data for and provide it at the highest resolution we can process it to. And doing it, we try to do as a climate record because we have data going back to the 70s, so people do climate studies with it. So I encourage you to go to our site and look at it. And I'll be glad to help you with interpretation. We've got 50 terabytes of data available online for people to look at and use. And we'll process anything you want, well, within our limits, if you need some special custom things.
Okay, thank you.
Any other questions?
Yes, I was just to follow on that. Can you describe the major users of the data so far, the groups and how things have been used? So follow on.
I'm not sure I can do that in a limited amount of time, but I'll give you some interesting examples. And I'm picking them mostly because they're interesting. Mm-hmm. So guys studying altimetry, sonar signals. Mm-hmm. So they're listening to the sounds in the ocean. They're studying whales, tracking whales. And they keep hearing these weird growling sounds. And so they trace them to volcanoes and icebergs. And so they use our data set, our iceberg database, to know where the icebergs are, to verify that that's from that source and not from a volcano or a whale or some other extreme thing. I thought it was the weirdest application ever. Guys doing altimetry, they're measuring sea surface level. And some of the French at CNES, C-N-E-S, I can't pronounce it. I don't speak French well enough to pronounce the real name of the institution. But they're doing this work and doing sea level rise. But the icebergs, when they run over icebergs or sea ice, messes up their tracking. And so they use our data set to verify that they have in fact detected an iceberg rather than some anomaly with their instrument or the data set or something like that. We've done a lot of work with people who want to study icebergs that we provide our data in real time so they can use their ships to navigate to the iceberg because they can move so quickly that they can't rely on everything. And once their radar gets close enough, they can track it. But to get him close enough is actually a little bit tricky. It sometimes takes them a week to get to these moving icebergs. And they track them because the icebergs carry nutrients, dust, and other things into the South Atlantic and the South Pacific, where they melt and cause algae blooms, which then bring in plankton, and then that brings in larger animals, and so become these islands of pelagic activity. And so we wrote some papers on this. I'm a collaborator on papers. We provided all the iceberg information. And so they fertilize the ocean, and eventually that the iceberg melts away, it goes away, all the critters die, they sink to the bottom, take some carbon with them. So it's actually a source of carbon sequestration, interestingly enough. But people want us to do the whales and the walruses. We did a whole lot of really interesting stuff this last year over Christmas time, because iceberg A68, which was a piece of the Larsen ice shelf, had been sitting there quietly, suddenly moved up into the Antarctic circumpolar current and did like B10A and shot over to South Georgia Island. And people thought it was going to ground against South Georgia Island. I said it wouldn't because it would hit the shelf, and sure enough it did, the continental shelf around it, but it did go around south. It might have gotten trapped in the eddy current that's behind that island. A10A, they did that before, and actually a lot of penguins and walruses died because they had to go around the iceberg to get to their feeding ground. But fortunately, it went around. We tracked this in real time. It caused a huge number of interviews and stories and everything else. I have a whole record of all these stories. We made movies and animations of the icebergs for people, and the National Geographic provide a bunch of data to the National Geographic, and our data forms the basis of their centerfold. So I told one of my students, who's a female working on this, that she's the centerfold of National Geographic. So she said, I never thought I'd ever be a centerfold before, but her data was the centerfold.
Very good. Yeah, excellent. That's very helpful to kind of get a feel for how this is used. Thank you.
Now we provide our data to people who are doing deforestation in the Amazon as well. You can imagine the ice tracking kinds of things we've done. The scatterometer data for winds is certainly used for just weather forecasting and climate data, the typical stuff. But this unusual stuff, there's a lot more that I could quote.
Okay.
Great Lakes ice, yeah. Tracking mosquitoes in Africa to predict malaria plagues by looking at the soil moisture that you can see as the lakes form. One of the more unusual things we've done.
Yeah.
Well, provided data for it. We didn't do that. Thanks, Peter.
Okay, very good.
Excellent diversity of applications.
Right.
I always say the scatterometer is really designed for other stuff, but we just can measure wind with it. And all the oceanographers get really mad at me when I say that, because they say, we designed this thing for oceanography to do winds. And yes, it does that.
Right.
But when I was at JPL, I designed all these scatterometers, and I get to use them now. It's fun.
Very good. Thanks.
Any other questions? Well, I guess we can thank our speaker with a round of applause.
Absolutely.
Thank you very much. And I hope you didn't mind me talking really, really fast, because I wanted to cover all this, give you something you could use maybe in your classes or something. So
yes, yeah, and great to see that you're making the data and the resources available. So thank you. Get that.
yeah,
link.
if you need anything special, let me know. We'll try and process it
Okay,
if we can.
sounds great. Very good.